Orbit is a constant fight between gravity and speed. A balance is needed to stay in orbit. We need to break the balance to deorbit something. This is pretty much what Earth's orbit looks like today. Not exactly, I kind of just sprinkled some red dots over a globe, but you get the idea. There's a whole lot of space junk. Earth orbits in a counterclockwise way when you're looking at it from the North Pole down. Because of this, we use the speed of the Earth's rotation to gain a velocity boost and therefore save fuel when we're launching something to space. In yellow, we are showing the direction the Earth is spinning, and in blue, the relative trajectory of a rocket. Once we achieve orbit, it is relatively circular, which means all points of the orbit are more or less the same altitude above the surface of the Earth. Because we launch all space junk in the exact same way, it's all flowing in pretty much the exact same direction. And you should note, this image is viewed from the South Pole. Most proposals today for deorbiting space junk involve launching in the same direction as the target junk that we're trying to deorbit. Here, the red dot with an arrow is what we're targeting, and the blue is the satellite that we are launching to deorbit that junk. The two pieces need to then rendezvous in orbit, which is fuel intensive for our deorbit satellite. Once they do, they're at relatively the same speed, and they need to slowly dock with our deorbit satellite. Once our deorbit satellite grabs onto the space junk, it needs to turn itself around and fire its engines in a retrograde manner, which means against the flow of its motion. Pretty much, it's slowing itself down. Once it slows itself down enough, it falls back into the atmosphere and burns up. What if we broke convention and deorbited satellites in a much more efficient way? Here's our target satellite. We launch in the opposite direction. This isn't as fuel efficient on ascent because we're going against the Earth's rotation, which means we have to spend a little bit more fuel and exert a little bit more force to get all the way into a circular orbit. We need to do no more fuel-consuming rendezvous once the satellite is in orbit and on a collision course with the space junk. Finally, once they collide, they're both atomized into tiny pieces. The force of the collision has also decelerated both bodies a significant amount so that both of them fall into the atmosphere and burn up. Another way of thinking about this is the force of gravity after the collision is now greater than the force that was propelling the two satellites parallel to the Earth's surface. The force of gravity didn't get stronger, but the force propelling them parallel did get weaker because they collided in opposite directions. But we can make this even more efficient. Once again, in this case, the red satellite is the space junk that we are trying to deorbit. If you'll notice, our satellite that we sent up to deorbit that space junk is now much smaller, approximately 1/10 the size of the space junk. After the collision, we can notice that our satellite is entirely destroyed and deorbited. It no longer poses any threat to existing operational satellites or manned vehicles in orbit. But what happened to the space junk that we're trying to deorbit? Even though our satellite was much smaller, the space junk still took a small hit in its velocity. Thankfully, a small hit in its velocity was enough to lower its altitude at some points in its orbit. Lowering it enough dips the space junk into the atmosphere, and air friction does the rest of the work. The satellite will burn up before it even touches the ground. So, what does the satellite look like? Well, one version could look like this. This is what many modern proposals look like. It includes an efficient engine, possibly an ion engine, and an antenna to communicate with Earth. This can be made even more efficient, though, if we add solar sails to the satellite. This reduces the need for fuel tanks or engines, as it takes advantage of the sun's solar energy to propel us into the final orbit on collision course with space junk. You can make these solar sails even bigger. As demonstrated by the Planetary Society, these incredibly lightweight structures can be unfolded once deployed into orbit and take maximum advantage of the sun's photonic energy to propel itself into a collision course with its space junk. This greatly increases the footprint of the satellite and therefore reduces the need for exact precision accuracy in targeting space junk, as it is likely that the junk will collide with any part of this satellite.